I want to design a mod 6 counter using T flip-flops. So what I will do, I will use a JK flip-flop and modify that for T flip-flop. So when J and K both inputs are tied together, it becomes a, or both inputs have the same input, it becomes a T flip-flop. That's what a T flip-flop is. So 7476, this chip is a JK flip-flop, and since it's mod 6 counter, we will need 3 bits, so we will need 3 flip-flops. So I will have to have 3, basically 3 flip-flops here. 37476. I won't go into the pin detail, but this flip-flop, this chip has a asynchronous clear, and what does that mean? I will talk about that a bit later. So JK, that's Q. There should be a clock, so maybe I will put the J bit up here, and then here the clock. So that's clock there, clock JK, and that's Q. Q bar will be there. I will not label that. So this is Q2, Q1, Q1, and this is Q0. So this one, Q2, is the most significant bit, and this one is the least significant bit. Now for a mod 6 counter, the counting should be 000, 001, 010, 011, 100, 101, and then it should again become 000. So up to here, this is just like an up counter. So this is Q2, and this is Q0, this is Q1. So when we look at it, so each of these changes happen with clock pulses. So for Q0, it's changing with each of the clock pulses. It's 0, 1, 0, 1. It's toggling. So what we need, Q0 should be changing with the clock pulses. We will make this counter synchronous. So all the clocks will be tied together. So here, there, this is our system clock. That's there. Now we want to, with each clock Q0, since it's changing, the inputs will be, T input will be in toggle mode. So J and K both will be 1. So we are just leveling. Maybe I will use a different color. I don't know. So 1, 1. Both J and K are 1 here. J and K. I didn't label that. So J and K. And this is of course clock. So that's there. Now when we look at the second Q1 output, we can see that in the first clock it's not changing. It's 0 here, 0 here. But from here to here, this is toggling. And this is again here is not changing. Here again it's toggling. So what we can say is when Q0 is 1, this is with the arrival of next clock, Q1 is changing. So if we connect Q0 as an input to J and K here, initially J and K here, so initially since Q0 is 0, J and K, J, basically this is J1 K1, this is J2 K2, and this is J0 K0. So J1 K1 is 0. So Q1, this middle flip-flop, is getting an input of 0. So it's no change, in no change mode. So this is not changing. But with the second clock, when this is already 1, when at this stage this is already 1, Q0, so the input J1 K1 here input, both inputs are 1. That means T flip-flop, if we think it in terms of a T flip-flop, we can say that it is in toggle mode. So the output will toggle. And again, after that this is 0. So J1 K1 input will be 0 again here. At this stage J1 K1 both are 0. So this is not toggling, this is staying the same because the input was 0. So the same thing will happen again. This one when this is 1, this is going to the input of j and k. So here at this stage j1 k1 both are 1, so this is toggling. So that's there, that is q1. Finally we need to look at what is q2. Now q2 is not changing up to here, it's changing only here, it's toggling only here, and that is happening when both q1 and q0 are 1, both of them 1. So what we should do, we should connect here q0, q1 and AND them and connect them as an input here. So for the first 4 clock pulses, q1 and q0 and combination will be 0. So j2 and k2 will get 0 as an input, that is the T flip-flop here. If we think it in terms of T, it is in no change mode, so q2 is not changing. But when both of them are 1, that is here, at this stage j2 and k2 is getting 1 as an input, so with the next clock pulse it is changing. This is not here, here this is changing, becoming from 0 to 1, because the input here, input j2 and k2 were 1, so this is the output toggles. So that's there. But this is just the operation of an up counter, and if we let it live, if we leave it like that, it will work as a 8-bit up counter, so sorry, 3-bit up counter, so it will count up to 7, 0 to 7. But we want it to count up to 5 and then go to 0. So for 6 clock pulses it should count. So what should happen, since now comes the clear function of the clear input. So when the outputs become 6, what should happen? The outputs should immediately turn into 0, 0, 0, because we don't want 6 to be displayed. So 6 means q2, q1 and q0. If we think like that, 6 is 1, 1, 0. So when 1, 1, 0 is output is becoming 1, 1, 0, immediately it should be fed back to clear in such a way so that each of the flip-flops clears. So the output becomes 0. So clear is an active low. I haven't drawn it, but for this IC is an active low. Preset is also active low, but we don't need that for this case. So all of them are 0, and they are asynchronous. When we say asynchronous, that means whenever it gets a 0, immediately the outputs, whenever we have a 0 here at the inputs, the output becomes immediately 0. It doesn't wait for the next clock pulse. If it were synchronous, it would have waited for the next clock pulse, but since it is asynchronous, it doesn't wait, so immediately it becomes 0. So we will be fine to apply 6 here, because whenever it's becoming 6, q2, q1 and q0, immediately it will turn to 0. So we won't be even seeing 6, it should turn to 0 and then count again up to 5 and then 0. So what we want here, this input to be all to be 0, when all of them to be 0, all these 3 clear inputs, when we have 6 here 1, here 1, here 0. So what we should do, if we NAND these two 1, 1, if we AND them, the output will be 1, but if we NAND them, the output will be 0. So unless here we have 1 and here we have 1, we can ignore this one. Here we have 1, q2 is 1 and q1 is 1. This NAND output will not be 0, and that will happen only once when we want it to be cleared, that is at this stage, which we don't want to be displayed, that is here 1, 1, 0. After 1, sorry, not here, it should be here 1, 1, 0. So after 5, so that doesn't happen. Q2 and Q1 don't become 1, both of them don't become 1 before in any other case. So this is the only case when both of them will become 1. And so if we use these two inputs and the output as the input of the NAND gate, the output will be 0 only when the Q2, Q1, Q0 is becoming 6. So that's what we should do. We should connect it here, I don't have enough space here, that's the problem. So basically what I'm trying to do here is NAND gate here, and I won't draw from the connection, so I will just label them here Q2 and Q1, Q2, Q1, and these two will be connected to all of the clears. This output will be connected to all of the clears, all three. So whenever this is Q2 and when we have 1 1 0, so Q2 is 1, Q1 is 1 and Q0 is 0, we don't have any Q0 input, that we don't need that. So when Q2 and Q1 is 1, both of them are 1, we will have a 0 here at the output of the NAND gate, so that will clear all the three flip-flops. So the counting will be stopped there, it will become 0 again, and then it will keep counting again. So this is how we can develop a mod 6 counter using T flip-flops, using a T flip-flop. So what we have done, we actually have used a D flip-flop, a JK flip-flop, and we have we have used it as a T flip-flop. That's what we have done. So yeah.